Welcome you all to NPTEl problem solving session. This is a live session for uh, all the topics covered in the course Introduction to Group Theory. This is an extra session, and in this session, we will summarize the concept in the course and we'll solve some problem based on it. So, I'm Priyanka Sharma, the PMRF NPTEl teaching assistant for the course. Let's start today's session. On the first question, we have a group with the identity element E and G and H. There are two elements in G with these two conditions. That is, G is a non-identity element and G square is identity, and H is also a non-identity element. H square is a non-identity element, and G inverse is H square. Then what will be the least positive integer n for which h to the power n will be identity? We need to find the value of n. So let's solve it. Here, this is given that g is not equals to identity and g square is identity. This is actually order of g is 2 and h is not equals to identity. H square is not equals to identity. That is, the order of h will be greater than 2. And we have another condition that G inverse is H square. So we need to find the order of H. So what if we calculate this? Okay, so actually we have H square is G inverse. If we square uh, both sides, or we can say that this will be H square is G inverse. G inverse. It means h to the power 4 will be G inverse G inverse, or h to the power 4, this will be GH identity G inverse. So this will be h to the power 4 is H square G inverse. Now we can again put the value of H square here. And this will become h to the power 4 is G, then G inverse, the value of H square, and this is G inverse. So this will be h to the power 4 is G square H G inverse square. Okay. But it is given that order of G is 2. Okay. And this will also imply that order of G inverse is also 2, or G inverse squared. This will give us the identity element. So this will become identity H identity. And this will be H4 is, so this is HE. Now, if we apply the left cancellation law here, we will get H cube is identity. So N will be 3. Or we can say that order of H is 3. Okay, now come to the next question. Given a, okay, this is all about, given a prime number P, let N P of G denote the number of p-silo subgroups of a finite group G, and which of the following is true for every group of order 202 2000+. So it's given that uh, G is a finite group. So let G be a finite group. Order 207. That is, it is up to us uh, which notation we want to use. They both implement actually. So order of G is 2024. If we break the order in prime factorization form, then what we will have um, will be 8, 23, 11. Okay. Just 22, 4, 11, and 23. That is, we have 3 primes in the prime factorization of order of G, 2, 11, and 23. That is, it will have 2 silo subgroups, 11 silo subgroups, and 23 silo subgroups. In the question, it is asked that what will be the number of 11 and 23 silo subgroups. So we will figure out only one. So let M11G be the number of 11 subgroups. And it is to be noted that the order of 11 silo subgroup will be 11 and the order of 23 silo subgroup will be 23. Okay, because in the prime factorization form, we have 11 to the power 1 and 23 to the power 1 as well. So then we will use the first and third Silas theorem here, and we will get that N11G. This will divide again the remaining part, that is 20 to the power 3 into 23. N11G. This is congruent modulo congruent to 1 modulo 11. That is N11G. This will be 1 plus 11 to the power 3, where 3 belongs to z plus 0, such that we have this condition also. Okay. So what can be the value of it? So if we have k equals to 0, for k equals to 0, we will have N11G as 1. For k equals to 1, this will be 12, but 12 doesn't divide 2 cube into 23 in this condition. Okay. So this cannot be possible. Now, what about k equals to 2? For k equals to 2, N11G will be 23. And here 23 divides this. So this can be either 1 or 23. If we take k equals to 3, k equals to 4, we can check that 1 plus 11k, that will not be a divisor of 2 cube into 23. So this won't be cases. So N11G can be either 1 or 23. It will depend whether the group is an abelian group or not. So if G is an abelian group, then then the 11 silo subgroup will be normal because every subgroup of an abelian group is normal. And if 11 silo subgroup is normal, then that will be unique. So if G is abelian, like this is a case, if G is abelian, and this can be a case if G is non-abelian. So if G is abelian, we cannot have N11G as 23. N11G can be 23 if and only if we have a non-abelian. Okay. So in the question, this is not mentioned whether the group G is abelian or non-abelian. So we can have both the possibilities. That is, N11G can be either 1 or 23. So we will consider both of them. Now, what about N23G? So let N23G be the number of 23 silo subgroups. Then again, we will use first and third silo theorem, and we will get that N23 of G, this will divide. So again, in the prime factorization form, we will exclude the power of 23, that is this. And what will be the remaining part? That will be 2 cubed into 11. So N23G, this will divide 2 cubed into 11. By Silas' third theorem, we will have that N23G, this will be congruent to 1 mod 23. That is N23G. This will be 1 plus 23 K dash, where again this K dash can be 0, 1, 2, or any non-negative integer. So you can say K belongs to Z plus 0 or Z plus Z. Therefore, what can be N23G now? Okay. So what if K dash is 0? If K dash is 0, we will get N23G as 1, and 1 divides 88. So it can be 1. Now, this is for K dash equals to 0. What about K dash equals to 1? If you take K dash equals to 1, we can have N23G as here 23 into 1 plus 1, that is 24. So 24 is not a divisor of here 88. So this cannot be a case. What if K dash is 2? Then again we can see N23G. This will be 23 into 2 plus 1. So again, we cannot have a divisor of this. Actually, its divisor can be 1, 2, 4, 8, 11, 22, 44, or 88. So we can get only one using this plan. Okay, it means out of these divisors of 2 cubed into 11, that is 88, only one is congruent to 1 under modulo 23. Therefore, N23G will be 1 only. So now, what will be the answer? Second one, that is N11G belongs to 1 and 23, and N23G is 1. So B is the correct answer. Come to next question. If G be a group of order 45, then G has an element of order 9, G has a subgroup of order 9, G has a normal subgroup of order 9, G has a normal subgroup of order 5. We need to check which one of the following is true. There can be more than one correct answers. So let's try. We have a finite group whose order is 45. 45 means p square into 5. Okay. So in the prime factorization form, we have two primes, 3 and 5. Thus, G will have 3 silo subgroups and 5 silo subgroups. So therefore, G has 3 silo subgroups of order p square, that is 9, because 3 divides order of G, 3 square divides order of G, but 3 cube doesn't divide order of G. That's why the order of 3 silo subgroup of G will be 9. And it has 5 silo subgroups also. Of order 5, because 5 divides order of G, but 5 square doesn't divide order of G. It means the option B is correct. G has a subgroup of order 9, and yeah, that subgroup will be silo subgroup. So till now we can say that option B is correct. Now, whether this subgroup of order 9 is normal in G or not, and what about this 5 silo subgroup, which is of order 5 in G is normal or not? Okay, so we need to check the number of 3 and 5 silo subgroups. So we'll use the same notation. Let N3G be the number of 3 silo subgroup. 3 silo subgroups means subgroups of order 9. Okay. Then we will have that N3G. This will divide. So again, we will remove the power of 3 from the prime factorization form. That is, we will have only 5. So N3 of G, this will divide 5. This is from the Silas first theorem. And what we will have from the Silas third theorem, condition that N3G, this is congruent to 1 mod 3. Okay. Now this 5 is a prime number, so it will have two divisors, 1 and 5. 1 is congruent to 1 mod 3, but 5 is not congruent to 1 under modulo 3. Okay. So this will imply that N3 of G can be 1 always. That is 3-silo subgroup is unique. And p-silo subgroup is unique if and only if that is normal. So from this, we can conclude that 3-silo subgroup, which is of order 9, is normal in G. That is option C is also correct. Now, what about 5-silo subgroups? So let N5G be the number of 5-silo subgroup in G. Then from Silas first and third theorem, we will have that N5G. This will divide. We will remove 5 and we will have 3 square root. This will divide 9 and N5G is congruent to 1 modulo 5. Now, what are the factors of 9? Um, Obviously, you will take positive factors. So, 1, 3, and 9. Out of them, only 1 is congruent to 1 under modulo 5. Okay. So, again, silo subgroup for prime 5 is also unique. The 5 silo subgroup is unique. And this normal also. So we can say that option D is also correct. Says that G has a normal subgroup of order. And in fact, G has a unique normal subgroup of order. Now, it remains to check the correctness of statement A, that G has an element of order 9. So, see, G has a subgroup of order 9, but does it assure that G has an element of order 9? If that subgroup of order 9, which is unique, is a cyclic subgroup, then only we can say that G has an element of order 9. But that subgroup of order 9, that can be non-cyclic. So in that case, G cannot have an element of order 9. So let's construct a counter example for that. So order of G is given as 45, or actually 3 square into 5. So let's split it such that we can have the subgroup of order 9 isomorphic to Z mod 3Z cross Z mod 3Z. Not to Z mod 9Z. Because in this case, we will always have an element of order 9. But the subgroup of order 9 can be isomorphic to this also. And in that case, we cannot have an element of order 9. So to do this, uh, we can write the group G as a direct product of two groups. And the first group in the direct product must have a subgroup of this form. So let's take this only. So This is Z mod 3Z plus the remaining part, and that will be 50. It will be Z mod 15Z. Now, it can have a subgroup isomorphic to this, but it has no element of order. Okay. Yes. Neither Z mod 3Z nor Z mod 15Z has element of order. Actually, it will have elements of the form, say, A comma B, where A is coming from Z mod 3Z and B is coming from Z mod 15Z. Okay. So what will be the order of AB? The order of AB will be LCM of order of A and order of B. So order of A will be computed in Z mod 3Z and order of B will be computed in Z mod 15. Okay. So actually, order of A can be either 1 or 3. Okay. So LCM cannot be. And this order of B, this cannot be. So option A is incorrect. So what is the answer? D, C, and D. These three statements are true. So actually, this was a question of multiple correct. So option B, C, and D, they are correct and A is incorrect. Now come to the next question. If order of G is 3 cube, then G is simple of. Okay. So here this is given that G is a P group. Their order of G is PQ, where P is a prime. Add this in the question itself. Where P is a so G will be simple if and only if it has only two normal subgroups, the identity and G itself. That is, G doesn't have any proper non-trivial normal subgroup. So, okay, we know that the center of a group is a normal subgroup. So, what will be the center for the group G? We know that a P group has a non-trivial center. Therefore, center of G is not equals to identity. Okay. And center of G, this is a subgroup of G, so that by Lagrange's theorem, order of Z of G divides order of G, as here order of G is finite. Then order of Z of G can be divisors of PQ, but it cannot be one. Otherwise, ZG will be the trivial subgroup, the identity one, and that is not possible. So this can be either P or P square or P. Okay. So if order of ZG, this is PQ, then what we can say that G is an abelian group. Therefore, all subgroups of G are normal. And order of G is PQ, where P is a prime number. So obviously G will have a non-trivial subgroup. So G is not simple. Okay. Now what if order of G is P square? Sorry, order of Z of G, that is P square. Then G by ZG, its order will be order of G by order of Z of G, that is P cubed by P square, that is P. It means G by ZG, this is isomorphic to Z mod PZ. That P is a prime. Therefore, this will be a cyclic group. That is G mod ZG is a cyclic group, which implies that G is abelian. But if G is abelian, then center of G and G, they will be same. That is, order of G cannot be P square, which is less than P cube. That is order of G. So this is contradiction in this case. That is, order of Z of G, this cannot be P square. The last possibility can be, which is corresponding to the case if G is non-abelian. Then order of Z of G, that can be P only, because it cannot be P square. Okay, it cannot be 1. That is, ZG cannot be identity, and it cannot be PQ. So there is only one possibility in the case of a non-abelian group, that order of ZG is P. Thus, for a non-abelian group, this is identity. This is ZG. This is G. Where 1 is strictly less than order of ZG, which is strictly less than order of G. And why I'm using this notation? Because center is a normal subgroup. So we have, other than the identity and G, a normal subgroup in G. So G is not simple. So if order of G is P cube, then whether G is an abelian group or G is a non-abelian group, G cannot be simple. So the statement is false. Come to the next question. Order of G is 36. Okay. And H is a subgroup of G. And order of H is 4. Then we have these 4 statements. And we need to check which of them are true. Is that. So given that order of G is 36, that is 2 square 6. H is a subgroup of G of order 4. Okay, so whether H is normal in G, H is an abelian group. First of all, since order of H is 4, and we know that every group of order 4 is abelian, because the uh, least group in the terms of order, which can be non-abelian, is a group of order 6. That is, up to order 5, we have abelian groups. And actually, G is of order 4. Sorry, if H is of order 4, then H can be isomorphic to either Z mod 4Z or Z mod 2Z cross Z mod 2Z, up to isomorphism. So option B is correct. Now, whether this H is normal in G or not. So let's check whether we can use Silas theorem or not. So let N to G First, let me see that G has fellow two subgroup of order 2 square. Okay, because 2 divides order of G and 2 square that also divides order of G, but 2 cube doesn't. So order of silo 2 subgroup will be 4. Now let N to G be the number of silo 2 subgroups of G, then N to G, uh, this will divide 3 square, that is 9, and N2 of G is congruent to 1 mod. So from here, N2 of G can be 1, it can be 3, and it can be 9 also. So we can't conclude from here. If we had only 1, then we can say that H is normal in G. But now we can't. So let's try in some another direction. Um, so G can have two possibilities. Either it is abelian or it is a non-abelian group. So if G is abelian, then center of G will be G. Okay. And as order of G is 36, so order of center of G is 36 also. Therefore, in the case of an abelian group, this cannot be true. Okay. Therefore, H is not equal to ZG if G is abelian. So we can discard option B here. Okay. Now, what about option A and option C also? So, in case of an abelian group, this is true that H is a subgroup of ZG because H is a subgroup of G. So, in case of abelian group, option A is true. But what if we have non-abelian group? So, let's construct something. And here we have, see, here we have order of G as 36. Okay. And we need non-abelian group. So if we break it as 2 square and 3 square, so For order 4, we have only abelian groups, and same for this 3 square. So what we should do, we should consider this as 6 into 6 because we have a non-abelian group of order 6. So split, that is, we need a non-abelian group of order 36. So let G is S3 cross S3 because S3 is a non-abelian group of smallest order up to isomorphism. So ZG, what can be center of this? So since center of S3 is identity, therefore center of G is again identity cross identity, we can say, or this is isomorphic to this. Okay. That is order of ZG. This is 1 here. And order of H is 4. So a subgroup of order 4 cannot be a part of the identity subgroup. So option A is incorrect here. It is incorrect. Now, what about C? So if the question is of single correct, then we can say this is true that H is an abelian group, but we can also find out whether H is normal in G or not. So for that, again, we need to consider some non-abelian group. So what in the case of S3 cross S3? So here, what are the normal subgroups in S3 cross S3? So identity S3 and A3S. Order of A3BB3. So yeah, that will be cited. Okay, so okay. Actually, to discard this, we need a subgroup of order 4, which is not order. Here it has order 1, it has order 6, and it has order 3. So we cannot have a subgroup of order here. What if we take something different? S3 has subgroups identity 1, 2, identity 1, 3, identity 2, 3 of order 2, and they are not normal because they like there is more than one subgroups of order 2. Okay, they are not unique, so they won't be normal. Now, what if we consider this identity 1, 2 cross identity 1, 3, which is a subgroup of S3 cross S3. Here it has order 2. It has order 2 as well. So I'm saying that this is H. Here, order of H is 4, but H is not normal in S3 cross S3. Because this is not normal in S3, this is not normal in S3, so the product will not be normal in the direct product of S3. So this is how we can discard option C. What is the answer? Option D. Okay. What is the next question? That uh, there is a statement. We have a group of order 30, which is simple. So is it true or it is false? So for that, we need to consider all possible subgroups of order 30. So let G be a group of order 30. That is, we are doing this. Order of G is 30. If we write this in the prime factorization form, so this will be 2 into 3 into 5. That is, we have 3 primes in order of G. Therefore, G has a silo 2 subgroup of order 2, silo 3 subgroup of order 3, and silo 5 subgroup of order 5. So the necessary condition for the group G to be simple is that the subgroup of uh, order 2, that is silo 2 subgroup, that should not be unique. Otherwise, that will be normal and that has order greater than 1 and less than 30. So that will become normal and G will not be simple. Similarly, the silo 3 subgroup of order 3, that should not be unique. Otherwise, that will be normal. And silo 5 subgroup of order 5. Again, that should not be unique. So that cannot be a normal set. So, okay, one thing, mm, G is an abelian group. Then all subgroups of G will be normal enough. Therefore, uh, therefore, an abelian group of order 30 is not simple. So that's why we assume that G is non-abelian. Because in case of an abelian group, the statement is false. Now, what about non-abelian group? Like, in general, we can say that the statement is false because mm, any subgroup of order 30, which is abelian, can be given as a counter example. Simply, we can give this Z mod 30Z. Okay, but if this is like G is non-abelian, if the question can be modified like this, then again we need to explore the possibilities. That's why we calculate further. See, what we need to claim that G is not simple, G has a normal subgroup. Okay? And G has a normal subgroup means uh, till now we have three types of subgroups in G. So at least one is normal in G, or at least one silo P subgroup for P equals to 2, 3, or 5 is unique. Okay, so we cannot say anything um, in an easy manner for silo 2 subgroup because P and 5 they are congruent modulo 1 and under modulo 2. Okay, so that's why we focus on silo 3 subgroup and silo 5 subgroup. Let N3G and N5G be the number of silos 3 subgroups and silo 5 subgroup of G respectively. Okay. Now, what about N3G? N3G will divide 10 and N3G should be congruent to 1 mod 3. Therefore, N3G it can be either 1 or it can be 10 also because 10 is congruent 1 mod 3. Similarly, N5G that will divide 6. And N5G is congruent to 1 mod rho 5. Therefore, N5G can be, um, what are the possibilities for N5G from the divisors of 6? This can be 1, this cannot be 2, this cannot be 3, but this can be 6 because that is congruent to 1 mod 5. So this can be uh, either 1 or 6. Okay. If N3G is 1 or N5G is 1. See, here we have two choices for N3G. That can be 1 or 10. Similarly, we have two choices for N5G. Either that can be 1 or 6. If um, either of them is 1, then we have a unique silo subgroup in G. So we have a normal silo subgroup actually in G, that is if N3G is 1 or N5G is 1, then G cannot be simple. I'm not saying that that will be simple because again we have N2Gs. But if either of these N3G and N5G will become 1, then this will sufficiently imply that G is not simple. So G can be simple. What is the necessary condition for G to be simple? If N3G, this is strictly greater than 1, and N5G, this is also strictly greater than 1. That is, if N3G is 10 and N5G is 6. Now, what we have? Uh, we have 10 subgroups of order 3 of the group G. And they are cyclic because 3 is a prime. So any group of prime order will be cyclic. They are cyclic. So how we can generate a cyclic group of order 3? We need an element which is generator of order 3. So a subgroup of order 3 has one element of order 1, that is the identity, which is common in all these 10 subgroups of order 3, and two elements of order 3. See, it has two elements of order 3. They are inverse of each other, and they both are generators for these cyclic subgroup. So as G has 10 subgroups of order 3, G has 20 elements of order 3. Okay, because any two distinct subgroups of order 3 cannot have a common element other than the identity. Because the elements of order 3 are generators, and two distinct subgroups cannot have a common generator. Similarly, we have 6 subgroups uh, that will be cyclic also, of order 5. So again, any group of order 5 will be isomorphic to Z mod 5Z, which is cyclic. So all these 6 subgroups of G of order 5 will be cyclic. And each subgroup of order 5 has one element of order 1, and all the non-identity elements will be of order 5 because it has 4 elements of order 5, or you can say 5 of uh, 5. That will be number of elements of order 5 in G, and they both will be generators of a subgroup of G. Elements of order 5. Therefore, G has each subgroup contributes 4 elements, and there are 6 such subgroups. So G has 24 elements of order 5 in G. Okay, so that order of G should be strictly greater than uh, these 20 elements plus 24 elements, because then we will add one which is for identity, and then we will add some elements of order 2 because we have 2 SSGs also. So that's why I'm saying this is strictly greater than this. Okay, because order of G will be 20 plus 24 plus 1 plus something. Mm. This means that order of G is greater than 44. This is a contradiction because order of G is given as 30. So this cannot be a case. That is both N3G and N5G cannot be greater than 10. At least one of them will be there. that N3G is 1 or N5G is 1, which implies that G has a non-trivial, proper, normal subgroup. Therefore, G is not simple. So whenever a group of order 30 is given to us, irrespective to the fact that the group is abelian or not, the group cannot be simple. So the given statement is false. Okay, come to another question, which is an interesting one. That is the number of non-isomorphic finite groups with exactly 3 conjugacy classes is equal to. We need to find the number of groups which has 3 conjugacy classes. And again, we are working in finite groups, and we need to find this number up to isomorphs. Let G be a finite group with exactly 3 conjugacy classes. Does it mean that we have 3 conjugacy classes for G? When we write the class type, we have 3 numbers here, okay? And all are in ascending form. Say here we have some alpha 1, here we have some alpha 2, here we have some alpha 3, then alpha 1 is less than or equal to alpha 2, which is less than or equal to alpha 3. We have something like this. Okay, so we can say, we can assume that um, the class equation of G, the order of G is 1 plus x plus 1. Or G has class type 1x comma y, or G has 3 conjugacy classes having 1 x and y elements in them. Okay. So why we took 1 here? Uh, Identity elements belongs to G always, and the conjugacy class of identity, that is identity itself. Because whenever we take something x e x inverse, this will be identity. So the conjugacy class of identity cannot contain any element other than identity. Therefore, the order of conjugacy class of the identity element will be 1. That is, in the class equation, the first entry will be 1. Okay. X and Y, they can be 1, they can be greater than 1, but at least 1 entry in the class equation or in the class types that must be 1 with respect to the identity. And without any loss of generality, we can consider x is less than or equal to y. Actually, it is because we are referring the corresponding class type by 1 comma x plus y. So this x can be less than or equal to y, and we can say greater than or equal to y. Obviously. Okay. So now we need to find the values of x, and since order of g is 1 plus x plus y, that is order of g minus x. This is 1 plus 5. Since x divides order of g by, because x represent the order of some conjugacy class, and um, like, order of all the conjugacy classes will be divisors of order of the group. So here we have x divides order of g, and yeah, we have y divides order of g as well. X divide order of g, x divide x also. So x will divide LHS of this equation. That is x divide order of g minus x. So we can see that x divides 1 plus y. Okay. And similarly, we can have y divides 1 plus x also. Okay. So what does this x divide uh, 1 plus y means? It means that x is less than or equal to 1 plus. And it means that y is less than or equal to 1 plus x. So now we have that x is less than or equal to y, and y is less than or equal to 1 plus x. So y can be either x or y can be 1 plus x. There is no other possibilities for y. Now we uh, deal with them one by one. So what if y it varies to x? Then order of g will be 1 plus x plus y, that is 1 plus 2x, or order of g minus 2x, this is 1. Now again, x divides order of g. So x divide order of, let me use same notation. X divides order of g and x divides 2x also. So x divide the LHS of this equation. Therefore, it can get this x divides 1. And x is mm, natural number, and this is greater than or equal to 1. Actually, this is order of some conjugacy class. X can be 1. And if x is 1, then y will be 1 also, because x and y, they are same. Thus, the class equation will be order of g is 1 plus x plus y, which sums to 3. Okay, so in the class equation, all the conjugacy classes have exactly one element, it means the group is abelian. And yeah, obviously, order of G is 3, so G will be abelian. So in this case, G is an abelian group of order 3, or we can say up to isomorphism. What can be G? Z mod 3. So there is only one possibility of G will be up to isomorphism. Consider the second condition, that Y is 1 plus X. Then order of G will be 1 plus X plus Y. So that will be 2 plus 2X. That means order of G minus 2X is 2. Hence X divides order of G. X will divide any order. X divides 2. X can be either 1 or what if X is 1? If X is 1, then Y will be 1 plus X, that is 2. The class equation will be order of G is 1 plus X plus Y, which is 2, sums to 4. But see, order of G is 4, and any group of order 4 is abelian. So all the conjugacy classes will have exactly one element in that case. Class equation of a group of order 4 must be 4 is to 1 plus 1 plus 1 plus 1, because there cannot be any conjugacy class having two elements. Okay. Therefore, X is not equal to 1 in this case. Thus, X equals to 2. And if X equals to 2, Y will be 3. Now, what will be the class equation? Order of G is 1 plus X plus Y sums to 3. That is, we have a group of order 6, and all the conjugacy classes are not of order 1, so this will be non-abelian. That is, G is a non-abelian group of order 6. And there is only one group of order 6 which is non-abelian up to isomorphisms. So G is isomorphic to S3. What is the answer? How many non-isomorphic finite groups with exactly 3 conjugacy classes can be? 2. One group can be Z mod 3Z and another one can be S3. Actually, I'm writing that's that's I can do. So this is next question. The automorphism group of Z2 cross Z2 is mm, whether this is Z2 cross Z2 itself, this is Z4, this is S3, or this is the trivial identity. So uh, this is the notation. The automorphism group of Z2 cross Z. Now, here we need to consider all the automorphisms, not only the inner automorphisms. Okay, so what it can be? Actually, Z mod uh, 2Z cross Z mod 2Z or Z2 cross Z2. This is A, comma B, where A and B belongs to Z2. So I write all the elements, then it will be 0, 0, the identity element of the group, 0, 1, 1, 0, and 1, 1. Okay, these will be the four elements of the group. Now, um, for any automorphism, F from Z2 cross Z2 onto Z2 cross Z2, we have F of 0, 0, it will be 0, 0 also because like image of identity under any automorphism will be there. Actually, this is true for any isomorphisms. Like identity of first group will be mapped onto the identity of second. So now we have these three non-identity elements. So automorphism means if we take the first non-identity element in the group. So this 0, 1 can be mapped either on 0, 1 itself or 1, 0 or 1, 1. Now, what about this the second element in the subcollection? 1, 0. So this can be mapped on to uh, the remaining two choices. Okay. And image of 1, 1, it can have only one choice. There are 6 automorphisms of Z2 cross Z2. Um, F belongs to AUT Z2 cross Z2. Then F of 0, 1. This can belong to 0, 1, 1, 0, 1, 1, f of 1, 0. This can belong to 0, 1, 1, 0, 1, 1 minus f of 0, 1 because we need bijections only. And this can be 0, 1, 1 minus f of 0, 1 and f of 1, 0. Okay. So from here, we can have three possibilities. From here, we can have two possibilities, and here we can have only one possibility. Okay. So that's why we can have exactly 6 automorphisms. That is order of AUT Z2 cross Z2. This is 6. So this cannot be true, and this cannot be true. Uh, okay, this cannot be true as well. It can be S3 only. So if we have these 4 options, then we can directly say that S3 is the correct one. But let's come back to this again. This implies that automorphism group of Z2 cross Z2, this can be up to isomorphism, either Z mod 6Z or S3. If this is abelian cyclic, and this is non-abelian non-cyclic. Up to isomorphisms, this has these two possibilities. So as per the options, this is true, but we need to check why automorphism group of Z2 cross Z2 can't be Z mod 6Z. So see, Z mod 6Z, this is abelian, but S3 is non-abelian. So it will be sufficient to check whether AUT Z2 cross Z2 is abelian or not. Then we can certainly say that whether this is Z mod 6Z or S3. So okay, consider two automorphisms. Take F1 from Z2 cross Z2 to Z2 cross Z2 defined by f of AB. This is 0, 0. If AB is 0, 0, we need to take images of remaining elements also. So So this is 0, 1. This is 1, 1, and this is 1, 0. Because we need some non-identity uh, automorphism so that we can check the possibility of non-commutativity. And F2 from Z2 cross Z2 to systematic inclusion. Z2 cross Z2 defined by, we need another non-identity automorphism here. So first element that must be fixed, if that is 0, 0. And to say this is 1, 0, this is 0, 1, and this is 1, 1. Clearly, both F1 and F2 are distinct and known identity as well. So we can check that this is F1 and this is F2. They are non-commutative. So let's check the image of 1, 0 under Billy. So this would be F2 of, so F1 of. What is F2 1, 0? That is 0, 1. What is F1 0, 1? That is 0, 1. What is F2 F1 1, 0? That is F2 of F1 of 1, 0. Uh, that is 0, 1. Means same. F1 of 1, 0. F1 of 1, 0. That is 1, 1. What is F2 of 1, 1? That is 1. So F1, F2 and F2, F1 gives different images for same element, so they cannot be same. It means F1, F2, F1 and F2, they don't commute with each other. F2 cross F2 is non-abelian. Means this is isomorphic to S3. Okay. Now, this is isomorphic to S3 means it will have 6 elements of, if I want to figure out them, since S3 is identity 1, 2, 1, 3, 2, 3, and 1, 2, comma should not be there. 1, 2, 3, and 1, 3, 2. So this is of order 1. This is of uh, order 2, and these two are of order 3. Okay. So see, and in this f of AB, actually f of AB gives AB if AB is 0. So this is fixed. We have 3 elements. Okay. See, if I want to write I3 on which I will mm, generate the computation. So this will be 0, 1, 1, 0, and 1, 1. Okay. So as we have I3 as 1, 2, 3, and then in S3, we take bijections from I3 to I3. So now we take bijections from this I3 to itself. Okay. And um, see, in 1, 2, image of 1 is 2, image of 2 is 1, but image of 3 is 3. That is, image of one element is fixed in 1, 2. Similarly, image of one element is fixed in 1, 3 as well as in 2, 3. So, see here, uh, image of this element is fixed, and here image of this element is fixed. So, if I say that this is 1, 2, and 3, so this F1 will be similar to 2, 3. Okay. And this F2 will be similar to 1, 2. Okay. Because this is similar to 1, this is similar to 2, this is similar to 3. So in 1, 2, uh, image of 1, 1 will be 1, 1, and image of 0, 1 and 1, 0, they will be interchanged. Similarly, we can define this. Now, what about 1, 2, 3? So in that, image of 0, 1 will be 1, 0, image of 1, 0 will be 1, 1, and image of 1, 1 will be 0, 1. Now, what about 1, 3, 2? In that, image of 0, 1 will be 3, means 1, 0. Now, image of 3 is 2, means image of 1, 1 will be 1, 0. And image of 2 is 1, means image of 1, 0 is 0, 1. So, this is how we can define all the 6 elements. Okay. And one more thing, if instead of automorphism group, uh, inner automorphism group was asked. In addition, inner automorphism group of Z2 cross Z2, this is isomorphic to inner automorphism group of any group G that is isomorphic to G by center of G. So this will be isomorphic to Z2 cross Z2 by center of Z2 cross Z2. And Z2 cross Z2 is an abelian group, so its center will be same. So this will be Z2 cross Z2 by Z2 cross Z2, which will be isomorphic to identity. Okay. So if here inner automorphism group of Z2 cross Z2, this the question was this, then 4 will be the correct option. But here answer is uh, so let's find inner automorphism groups of these two groups next. Hence, inner automorphism group of G is isomorphic to G by ZG. So in the first one, inner automorphism group of S3, this will be isomorphic to S3 by center of S3. So what will be center of S3? Center of symmetric group of degree 3. This will be the identity group actually, because only identity permutation is the permutation which commutes with all the permutations defined on cycles. So this will be S3 by, here we will have identity, and this will be isomorphic to S3 again. So inner automorphism group of S3, that will be S3. Inner automorphism of Q4, that is quaternion group of degree 4. That will be Q4 isomorphic group. Center of Q4. So what is center of Q4? Center of Q4, we have two elements, 1 and -1. That is order of inner automorphism group of Q4. That will be order of Q4 divided by order of this group, 1 and -1. That is, we have 8 elements in Q4, and here we have 2 elements. This will be 4. That is, order of inner automorphism group of Q4 is 4. So this can be isomorphic either to Z mod 4Z or Z mod 2Z cross Z mod 2Z.